Professor in the Department of Computer Science and Engineering at Indian Institute of Technology, Banaras Hindu University. Previously, she was as a researcher in TCS Research and Innovation, Bangalore, India. Her area of specialty is the interest include deep neural networks, computer vision, human-computer interaction, pattern recognition, multimedia forensic, and Internet of Things (IoT). She has guiding over 10 PhD research scholars, junior research fellows, and project officers, besides guiding 50 plus of masters and undergraduate students. She has established Innovation Lab Bangalore, research collaboration with the Samsung R&D Bangalore, Samsung R&D Noida, IBM, TJ Watson Research Cyber USA, National University of Singapore, University of Chicago, Missionary University of Science and Technology. She has undertaken over 6 research projects in India during the last 5 years, sponsored both by national and international agencies, worth over more than 1 crore. She has published over 100 research articles in various journals, conferences, and workshops of high acclaim, and she has organized numerous courses, conferences, seminars on her core areas of experience. She has 5 patents, 2 patents with the TCS Research Innovation Lab, and 3 patents with IIT BHU. She was the recipient of the SAIL undergraduate scholarship for pursuing her BTech degree, and her PhD was supported by the TCS Research Fellowship. She won the Outstanding Paper Award for TCS Research and Innovation India 2014. So now we have such expert for our today's second session. So I invite ma'am to kindly share her lecture with us and enlighten. Please, ma'am.
Is it visible?
Yes, ma'am. Yes, ma'am. You are visible.
Then the lecture is the slide is visible.
No, the slide is not visible. Please share it.
Now it visible?
Yes, ma'am. Yes, ma'am. Now it is visible.
Okay. So thank you, Dr. Singh. Let me start it. Okay. So good afternoon, everybody. I, Dr. Tanima Dutta. Today I am going to present a seminar on deep learning architectures for digital watermarking and multimedia forensics. So I want to thank Dr. Singh for inviting me for this lecture on the FDP on cybercrime and computer security. So today initially I will start with the basics of deep learning architectures and the digital watermarking. Then I will elaborate the traditional and the recent techniques on digital watermarking. Finally, I have discussed a bit about myself as well as my group, which all of us were working on deep learning architectures in computer vision problems and in digital forensics. So in the end, I have my mail ID. If you have any queries in future, you can contact me from through this email ID. So what is deep convolutional neural network? So there are 3 keywords. One is neural network, then convolutional neural network, and finally deep convolutional neural network. For neural network, we know that if you can see these FC layers, this is fully connected layers, 6 and 7. If we say this thing, this is we call as a neural network, where we have neurons, and there are 2 layers of neurons, and these neurons may represent the pixels or pixels of the images, or may represent the features of the images. It depends how we are presenting them. Now, when they are interconnected, they will explore all the features in all possible ways. So basically, if we say neural network or artificial neural network, there are neurons which explore the features. Next, but the thing is that if we see the images or the videos or some multimedia objects, we'll see that in there, if you just see any image, you will see that there is a lot of correlations. That means there are a lot of relatively similar type of things in the nearby region. So if the correlation is very high, why should we take the advantage of the nearby correlations? So then the idea of convolutional neural network has come up, where we have convolutional kernels. So the kernels will have different sizes. It may be a window of 3x3. It can be a window of 1x1. It can be a window of 5x5, 6, 7x7, 9x9. Generally, we keep it as an odd number because we can get the middle pixel, and the middle pixel will be evaluated based on the neighboring pixels of that window. So the next part is, after that we come to the keyword deep. So what that deep means? The deep means basically the number of layers. There should be a multiple number of layers between the input and the output layer. So therefore that only means that we have more and more convolution layers between the input and the output layer. So this is just a simple demonstration of any convolution neural network. So here we have the input image. The input image can be an image, RGB image, can be a video. So it can be a 3D video. It can be depth images, like if we have depth information. It can be optical flow information. So for motion information, we extract the optical flow. So it can be like that also. So whoever worked on related to image, they know that RGB images, depth images, and the optical flow information that are quite easily available, and that are almost like people who are working in image processing, they are also working it earlier before the coming of deep convolution neural network. So in short, I will call it as deep networks. So what are the popular architectures that are used? So the people used to make their own architectures. They used to typically design the architectures based on their utility, but still there are few architectures which are standardized and widely used. So some of this type of architectures are, we'll take it like, let's say VGG16. So VGG16 is basically an architecture that has 13 convolution layers and 3 dense layers. So it is one of the very good and popular architecture. Many people use this architecture when we have a shallow network. What is called shallow network? Where we know that we don't have to go very deeper in the architecture. So there that network we call a shallow network. So VG16 is it's not less than 10, so it's not a very shallow network, but it is not very big, like let's say a ResNet 101. It's a very big architecture. Okay, it's only VGG16, so it has 13 convolutional layers. Apart of that, we have ResNet 18, 34, 50, 101. In ResNet 18, we have 17 convolution layers and 1 dense layer. So it also have skip connections and residual blocks. There are AlexNet, MobileNet, single sort detector, generative adversarial network. These are very, very popular networks that are used in deep neural network. Now, where the deep neural network is used. So if we say where it is used, it is really difficult to count where it's not used. Nowadays, it almost in all the fields in multimedia, let's say starting from audio to image to video, in every field it is being widely used. Apart of that, it also it can be used in networks. It can be used in it is widely used in NLP. It is used in many, in AI, in all the areas where AI can be used. We can use this deep neural network. So deep neural network is an advance of machine learning where we have used neural network rather than using the other learning techniques. So I will come in details of that a bit later. Now we have what are the applications, like image segmentation. So earlier we used to do image segmentation using different of clustering techniques or different other techniques we used to do. Here we are using deep neural network to do image segmentation, action recognition, image captioning, video summarization, syntax detection, image stylization, image restoration, etc., etc. So there are it's like I'm just giving only a few fields to you. There are lot other fields. I'm mainly mentioned all the fields that where I'm currently working in. Now, why deep network? Why not other? Why? What is the problem with our feature learning techniques using image processing technique? Using image processing. Now, if you see there is this image, you can understand when we are doing image processing, we used to give some filters. Normally, that filters will run over or there are some techniques like that where we will take the features and assume that okay, this can be that. Now, if you see, there's a dog and a fried chicken. They are almost if you see it's really indistinguishable if you only go for normal deep learning techniques, as normal image processing techniques. Not only that, if you go for machine learning techniques, then also it is not very good. Why? So in machine learning techniques, what we do is we as a human being provide the features to the tool so that the system can learn based on the features and finally give the output. Let us assume that we have the label, that is these are supervised learning. Even I said that the first one is a dog and the second one is a chicken, is a fried chicken. Again the third one is a dog and it was again a fried chicken. It is really when I say they take the features, I will take these textures, I will take these areas like that, but it is really difficult for the system to learn because they are very similar in terms of texture, in terms of RGB values and all the things. So there it's the complication. This type of images or videos create lot of complication. Similarly, there is another, it's a puppy with a bagel. You can see that here also the images are so similar that is really, if I provide our own features, it is become very difficult to distinguish even the features are given and to learn the system. I have quite some more images, like this is a mop and a sheepdog. Then I have, this is a chihuahua and a muffin. If you can see, they look similar. If we, except we human, it's really, for a machine, it's really difficult to detect because what they will do, they will see that there are some black spots, there should be some brown colors. These things all they will do. They will take the distance between the black spots, that the Euclidean distances, but it's still very difficult. But unknowingly, we human can detect that this is a dog and it is a muffin. So we use our own knowledge. So how we use our knowledge? So that creates the difference. So that idea, how human use their knowledge to identify this type of complicated images. So I have few more, like this is an owl and an apple. So that idea has been extracted and has been used in neural network, deep neural network. So why idea thousands and thousands of images of similar kind. Okay. And maybe if you have thousands and thousands images, I will not give the features to the system to learn. Rather, I will say the system learn from these thousands and thousands of images. So that maybe we persons can be biased. We cannot look for all type of features. These type of all possibilities can come up. But when the system learns with a huge number, let's say 1024 number of kernels, 1024 number with kernels, and let's say it have 10,000 of images of similar kind. So obviously, in all possible, using all possible type of filters, it was acting on all type of images and finally making the feature vector. So there, the possibility of missing something will not be there. So obviously, if it is like that, then in that case, the human intervention of giving features is not a good idea. So there the advent of the deep neural network has come up, from the machine learning techniques. So machine learning in the let's say 10 years back was very popular, but now after let's say from 5 years back, the deep learning techniques has become more popular when they found that getting data is easier, but making a fine tune and very perfect feature is tougher for this complicated scenarios or images, I'll say. So then the neural network is become more popular than that of the machine learning techniques. Obviously, there are challenges. There are different challenges. The first challenge, if I say, is obviously the huge of data. So prior to the challenges, I will come to what are different type of learning techniques. So supervised learning, unsupervised learning, and semi-supervised learning. So even these three topics are also same for the machine learning techniques. Supervised learning techniques means we have huge data, but all the data are labeled. So label means if I say this picture, I will say, let's say this picture or this picture, I will say this is an owl and this is an apple. So it was labeled that this is an apple and this is an owl. So that labeling is done manually by someone has said, or we have from crowdsourcing somewhere, but the labeling has been done for each and every image, so that when the system learn it, they should know for which level what they are learning. Okay. Now next is unsupervised learning. The unsupervised learning is basically where the supervised learning is difficult to train. That means, let's say if you go for data, you will see there are a lot of data, but they are not labeled, and it's very practical because who will sit and actually label the data? It's really a tedious job, right? So it's not easy that someone will sit, because see, nowadays we are all morely reliable on the internet. So we do lot of access, we do lot of things over. We use mobile phone, use different of softwares, we use different type of apps, right? So we do a lot of things, and most of the things are being temporarily saved in some of the servers. So there's no limitations of data. We can get huge data, but who will sit and actually label them? That is the challenge. So there, some people at that time then say that if we can have methods where we don't have the label, but we have a huge of data, and can we learn from the data? Like, let's say if we human being, if it is not said it's a dog, but if we see hundreds of dogs, we can see these are of similar kind. These are an animal which is of similar kind. I cannot say a cow and a dog are same, because the cow and the dog are not labeled. I will never say that, because though I don't know that it's the name of the animal is dog, but I can get pardon? Any question? If you have any question, you can stop me and ask me there. So yeah, unsupervised learning. So if I have millions and millions of data, let's say, so we human, if we see two dogs, we will know that though they have different kind of dogs, but still I can recognize them that they are dog. At least if I don't know that the animal name is dog, right? So this type of learning techniques we have. So now people, though in the, I will say 2 or 3 years back, this unsupervised learning was not so popular, because the supervised learning give a really excellent results, whereas unsupervised learning, the results and accuracy are not so good. But nowadays, there are some issues that come up that I will, maybe in next slide, I will discuss the issues with the supervised learning techniques, where nowadays recently, let's say for last 1 year, it's become very, supervised learning is again gaining popularity, because we have lot of data which are not actually labeled. The last one is semi-supervised learning, which is also very popular. Let's say whenever we, since this workshop is on cyber security, you can understand that, see, we are using lot of data, this network flow. Okay, the lot of data is on the network and the routers. If we can access on this data, we can have, though there the headers footers will be, if we remove also, still we'll have lot of data, but obviously the data are not labeled, so we can use them. We can use them for our analysis, let's say network flow or something like that. Okay, or what type of data has been bound, whether they are spam data, whether they are normal data, all this time we can analysis we can make. But if we say that if we only go for unsupervised learning, since we have lot of data and they are not labeled, then it has become very difficult, because without any label, we make different categories, but what category it is not known. So the technique that was said was semi-supervised learning, which a few of the data are labeled, whereas most of them are unlabeled. So based on the few of the data which are unlabeled, which are labeled, the rest of the data which are similar and unlabeled will be utilized, and finally a very strong feature vector will be formed. So obviously still we are in the supervised learning techniques. I will rather say most of the people are working still with this supervised learning. Few people work on unsupervised learning, and few more people are working on semi-supervised learning. Those who are actually working with big data, or I will say where the data size is very huge, whether then they go for semi-supervised and unsupervised learning. But where we have limited data sets, obviously that limited is not like 20 or 100 or even 500, it is obviously in thousands, but still they look for semi-supervised learning. Now what are the key challenges? So first key challenge, as I already told you, that we need enough quality data. First is data, then huge amount of data, next is quality data. So obviously we need data, and if data should be huge, because we are not providing any features to them, they are learning from the image itself or from the multimedia object itself. Now why the quality data? Because though we are providing labels, still let's say the images are very blurred, the images have lot of noises. Obviously if it is like that, then the features will be diverted. Exact features I will not never get from there, right? So the quality of data is also matters a lot. So obviously we can afford some amount of noisy data, keeping that mind that it should not be overpower over the non-noisy data. So we have to keep in mind that thing. Next is overfitting in neural network. Now there is a very common problem is that whenever we make a data set, let's say if you have got a data set, it's fine, but if you want to work in some area where the data sets are very limited, so you want to make your own. So what the biggest problem that come up is the overfitting problem, and the overfitting problem comes when we have the class imbalance. So some of the classes have lot of data, while some of the classes has very less data, because when we search we get some classes very common and we get lot of multimedia, image, video or objects or audio, images and videos, but for some classes we get very less. Let's say we take an example of action recognition. For action recognition we have different type of actions, let's say sitting, climbing, running, all type of actions are there. Now eating, it can be like that. Now I say something like he was some very uncommon action which is not very rare, which is very rare. Okay, so then that type of actions we really will get very less amount of data. So the common actions like sitting, running will get lot of data, but if I go for something very uncommon, someone like who is very surprised is still okay. Let's say some other actions where someone is actually showing a thumbs up to someone. So thumbs up is, again we have to search a lot of places and then we get some thumbs up maybe. So it's really a very uncommon that people are showing thumbs up when he is happy and showing a thumbs up. Okay, so this type of actions, if I say, it's really very difficult to accumulate data for that. So there the problem of class imbalance will come up, and once the class imbalance problem will be there, and if you train with such a data set, obviously overfitting in neural network will happen. So there are some solutions are there. First is obviously we have to look for the class imbalance problem. Another thing is that apart of that also, sometimes it happens that it was not working properly. Still the validation accuracy and the training accuracy are very different. So normally if you do actual training on neural network, you will see that we always look for the validation accuracy as well as the training accuracy to find whether there is overfitting or underfitting is there or not. In that case, we use some dropout, we use different optimization techniques, we use some activations, all these things we try our different all other things. Apart of, obviously, first we check for the class imbalance is there or not. If it is not there, then we look for the other possibilities, how to overcome with the overfitting problem, or we increase the data in the data sets by merging multiple data sets so that the overfitting problem should be removed. Next is requires high performance hardware. Oh yeah, this is another very big problem. If you even take a small data set, let's say I will say 100 images, and let's say the image size is of 224 plus 224. I think you can understand it's a very small image. Even it will take, let's say, 15 GB kind of thing of GPU. So it will, when it will actually, the features will be scattered, features will be extracted and will be saved in different pickle files. It will be really a very big size. So obviously we need GPU, we cannot work on normal systems. Again, if you have system GPUs, that means you need some servers. So there are high performance hardwares. So it's now, there are some softwares, there are some applications, not software, applications are available like Kaggle, then Google Colapse, these are available, but they are also very limited. Their access is very limited. You can do one, you can access one program at a time. You can have only this amount of data, this amount of RAM is available. These are nowadays are available, but still it's really a tedious job if you have a big data set. And even before, if you have a deeper network, then that is really worst. Prior to deeper network, we have just, if you have a very big data set, it is really working bad. You will continuously get segmentation fault, memory exhaust problem, all these things will come up. Now if you have a deeper network, and that too if you have along with the size of the kernels are bigger, it's not, let's say it's a 5 plus 5 or 7 plus 7 kernels are used, so then really tedious job, because anyway the input size into output size into the size of the kernels into size of the input and output channels will be multiplied together to form the number of parameters for a convolution layer. So really it is a difficult task. The next problem is hyperparameter optimization. So obviously it is a part of another overfitting in neural network, I will say. So there are a lot of parameters. Let's say optimization, what type of optimizers you are using, whether you are using dropout or not, what type of lexicons you are using for labeling. Okay, so if you are using regression, how you are actually assigning the coordinates. Next, what type of activations you are using, what type of cost function you are using, whether that is sufficient or not. Is the loss function is sufficient to look for all the output that you are looking for? Lot of things are there. So all these parameters need to be optimized and properly for to get the best accuracy when you are doing any work with the neural network, whether it's a action recognition or let's say it's a image segmentation, whatever it is, but you have to take care of your network. Next is neural networks are essentially a black box. Yeah, that is again a problem. Like normally if you do image processing, we can say if I do some erosion or if I do some other task, let's say if I am doing some transformation, I know this will be mapped to that exact mapping will be with us. But in neural network we normally use APIs, and that APIs have, if I say there's 64 filters, any of the 64 filters out of, let's say it has 2000 or 3000 filters, it will take up any of the 64 and we use them up. So it's very difficult to say, okay, this exact output should come immediately after one convolution layer. So it is essentially a black box. We can manually see, we can manually make a box and try it in our copy, but we cannot estimate that exactly that result will come up. So that is obviously again another challenge. So we always rely that if you will, that's why how we will solve this problem. Normally what we do is we make multiple iterations. We will not do only a few iterations. We may let's say we train with 250 or 300 iterations, and for each iterations we have some few epochs, and then finally we get whatever the results we get, out of which we say, okay, this is the final result that we have got. So all possible combinations should be worked out. The last one is the lack of flexibility. So obviously we all know, those who have worked a bit of deep networks, they knows that in deep networks we always train with a particular type of data. So obviously it cannot be, a network cannot be a general. The network is general, but when you train it, we train it with a particular type of data. So it is not a general. Obviously it will predict that type of data only. In the test case, it will not go for predicting each and everything, right? So obviously this lacks the flexibility. Now, what are convolution operations are used? So in general, we use k cross k convolution kernels with n filters as an input on an input of h cross w cross c. So that is a normal convolution that we usually perform. So we take the input of h cross w cross c, we keep the kernel as k cross k, with n filters will be output. So c will be changed to n. And in general, to keep the number of parameters less, we keep the k cross k as 3 cross 3. But still the getting a working model in a normal server, I'm saying, okay, not a high performance computing, normal servers which are GPUs, it's really still difficult. So there is an architecture called MobileNet that I mentioned earlier, where there are two other type of operators are used, pointwise operator and depthwise separable operator. So in most of my work, I prefer to use MobileNet architecture so that it can be actually implemented in the servers. So that I can put a constraint on the number of parameters while designing it. So what is pointwise operator? So pointwise operator, basically it uses 1 cross 1 filters while changing the number of filters from C to N. Whereas there is which should be followed by a depthwise separable operator, which will have a kernel of k cross k that we used as 3 cross 3, where the number of filters are not changed, but it convolve over the image and get the neighborhood information. So I have given the reference of MobileNet v2. So each of the layers we break the one convolution layer as follows. So first the input is h cross w cross a k, which is break into first 1 cross 1 convolution, where we have changed the number of channels or the number of filters, I will say, k to tk. So t is the expansion factor. Then keeping the same output as the input for the next layer, we have used depthwise separable operator, where the kernel size is 3 cross 3, and we have convolved it with a stride. Also we have used a stride, or in place of stride you can use max pool also. So it is h by s into w by s into tk. Next, taking that as an input, we have used linear 1D to convert the number of channels from k to k dashed finally. So k to tk, from tk to k dashed. So this is the operation that MobileNet v2 has performed to break one convolution operation. So normally the architecture they have 19 residual layers. All these bottleneck are called the residual layers, where t is the expansion factor, c is the number of channels, n is the number of repetitions, s is the number of strides. So they have normally take the input, because this is a architecture for images. So in images we normally take the size, the input size is 224 cross 224 cross 3. For videos we take a smaller size, because again videos have temporal length. So obviously if they have temporal length, they are more huge in nature. Okay, because if I take 100 videos, obviously per video if I take very limited frame rates, let's say 30 frames per second, then also it will have 30 frames for each second. And if they, let's say if they continue for all 30 seconds, so it will be 30 into 30, right? So it will be 900 frames for each of the video, right? Each of the video clip I will rather say, because it's a 30 seconds, I hope you can understand, it's a very small video. Anyway, here I am just taken architecture for the MobileNet v2 for the images, where this architecture mainly we widely use, because so that we can actually train the systems in the servers, not high performance computing but good servers, I will say, which are GPUs. Okay, and also they have removed the fully connected layers, because fully connected layers are again very computationally expensive. So they have removed the fully connected layers with the average average pool, GAP, or I will say global average pooling using 7 plus 7, so that we'll get the finally a 1D vector kind of thing, and that 1D vector will pass for the classification. Now, some of the important architectures that are widely used is the one of the, normally till now we have talked about only where we have given the input, and it will in sequence, it will be squeeze in resolution and increase in increase in the channels, and finally we will get a 1D vector, and that vector will be feature vector. That one feature vector will be used for classification. But still this is not sufficient for lot of operations where we need multiple resolutions. Let's say that when there are the images are very complicated, we need multi-scale images for classification. So there the idea comes is the convolutional encoder decoder architecture. So this encoder decoder architecture, what they have done is, first we squeeze the feature map and increase the channels. Next we again expand, we use deconvolution operation or unpooling to expand the resolution, mostly keeping the channel intact. That is the channel that we have in the last layers. We normally keep the channel same. Now here, what are the advantages we have? First is, if you see the results of each of the convolution layer, you will find in the initial stage of the convolution layers, we will have the low level features, that is edge detection, boundary detection. All these things will come in the initial layers. Next, in the high level, we'll have the semantic, that it is what object, that is the bound, that is the it will have the complete object information. So that type of features are present in the final layers. So what the encoder and decoder will do is, it will help to capture both the low level features as well as the high level features. So we'll combine these lines are the basically lateral connections. These lateral connections will help to combine both the high level as well as the low level features. So what does it help? First thing, it helps from degradation problem. What is degradation problem? The degradation problem is like that. Let's say when you have very deep architecture, let's say inception model or something like that, we have very deep architectures. People initially, like 2-3 years back, they are all are looking for making more deeper and deeper architectures. So if you go very deep architectures, they found there is a problem of vanishing gradient. When it's very deep and the same feature map is again convolved, what will happen? After some time, the values will start vanishing. It will become 0.0000 something. So there will be no gradient will be found. There will be no change in values will be found, because it becomes very small, so small that the change in values will be really difficult. So if there is no change in values, then obviously when you do back propagate, it will not be updated. So that actually was the case. So whether we should go deeper or not, then the idea has come up, we should add some nonlinearity over there. So one of the popular nonlinearity is adding ReLU activation. There are some other also, like TANH, layered norm. There are some others also, like sigmoid activations, or some people also use them. Some logarithm activations are there, exponential activations are there. There are a lot of others are there. But the simplest and the most popularly used is the ReLU, rectilinear unit. So ReLU activations they have tried to add so that they can minimize the so that once the activation, once this nonlinearity has been added, obviously the value which are actually gradually becoming vanished due to their monotonously multiplication now will sustain some time. So then there is an architecture called ResNet has come up. What they have done is, they said, okay, what we can do is we use skip connections. Based on the skip connection, if the network does not need all the layers, we'll skip them. We'll skip some of the layers. So for them, almost 50% of the bottleneck layers, 50% are with 50% layers are with the skip connections. And I'm saying out of if I take there are 2 layers, they make a 1 skip connections out of the 2 layers. So any one of them can be used, kind of thing. So, so that was another way where the this degradation problem is solved by using the skip connections in USNet. Similarly, so the idea is like how we can add non-linearity. So when there are skip connections, obviously we are taking initial values. So it is again multiplying with the skip connection and we are skipping some of the layers. So that will add some non-linearity. Similarly, if we have skip connections, apart of skip connection, what else we can do? We can add ReLU, we can have skip connection, what else we can do? So next is we can use the encoder-decoder architecture. So in there, since when this low level features are concatenated with high level features, obviously the non-linearity is added. So that also helps to solve the problem of degradation. So that is one of the motive of doing encoder architecture. One is to get the low level features. Let's say you want to do something which need the low level features. Let's say you want to do a text detection, and when a text detection, the text edges are very faint. So what you will do? What the aim you should have? You have to capture all type of text edges. So if you only go for high level features, what will happen? The faint edges will be vanished. No one can capture them. So you have done, okay, I will do a edge supervision in the initial stages of the neural network. So obviously if you do edge, because in the initial stage then all the type of edges are there, whether it's faint or not, and in that edges you have actually add this supervision for the you have used the binary edge supervisions, and then if you put it in, if you keep it, if you take it from here to obviously in the higher layers, obviously that edge has come up. Now when you do classification after this, the edges are already there, the faint edges are also already there, because you have done some edge supervision over here and bring it over here, and now it has been finally, while classification along with the high level features, this low level features with supervision is already there. So now you can detect the texts which are also fainted. So all these are utility. There are lot of utility of the conventional encoder decoder architecture. Now next, another important part is generative adversarial network. So generative adversarial network is widely used in a lot of places like image restoration. Next is I will discuss this network because there's another reason is in our digital watermarking, this adversarial network is also very important. Because what happens in this network, the main idea of this network is to clone something. So what happens is there is a generator who will make the clones, and there is a discriminator which is trained with the trained data set, and it will say how close the clone is with the actual image, and it will also find the losses, so that will say whether it's a real or a fake. So this architecture, so obviously this is a neural network, again this is also a deep network, this is also a deep network. This is a deep network to clone the images, to make a clone of the images, and this is a network which says how good the clone is or how bad the clone is, whatever you can say. So this is widely used for image restoration, then I will say image stylization. In all these places it is widely used. Apart of that, in our cases, like I'm saying here, I am talking about digital watermarking. So there is a very popular attack called ATAL attack, who would try to sense the watermark image and to create an image which is almost similar like that, or I will say similar like that without watermark. So this usually work as an attack for the normal watermarking techniques. So it is widely used. I hope I have briefly discussed this. So this is what they have done. I'll briefly discuss it more. So this is some pattern. This pattern taken from some pre-trained data sets. Okay, so that pattern will be used continuously with will be used here in the generator. The generator will develop a model out of that. That model will be the output will feed to the discriminator. The discriminator will take the training data set as well as the generator produce output, and it will use the neural network and say whether it's a fake or real, and out of that you will obviously get some classification values. That classification values will be again feed to the generator, and based on that he will again repeat the network and fine tune the fake result, and it will again give the discriminator that result. Again it will compare, again it will do the classification, and based on the classification again it will come to the generator. So this way the process will repeat until and unless it will become a real. It will give a classification of a real data. Okay, any questions? No. The last one. So this is also very widely used nowadays. This is not a, I will not say that this is a model from the basics, rather it is a attention model. So this attention model is called squeeze and excitation network. So what happened is, let's say I am doing a task like human object interaction. So if I am doing a task like human object interaction, so obviously I have to know this is a human, this is an object, and how they are interacting. So for that reason I have to find, okay, this is the human, I have to find this is the object, right? So one way to do is I use some ROIs. I found the I used two ROIs, and from the ROIs I have taken the human and the object, and finally I use some FC layers to find the interaction between the ROIs. This might be one possibility. Now apart of that, what else can happen? I can give some add some activations on the edges of the where the human and the objects are interacting. If I give some activations there, or if I say whether this because there may be lot of images in between in the data sets where there is no human, there is only object, or there is only a human, no object. So it will be confused, like every time whether there is a human is there, and whether the human while estimating the human object interaction, whether the object is present or not, whether the human is present or not. If we can go for that, then obviously relation will be better. Otherwise, there is a lot of false information will come up. It may mislead the results. So if I can detect whether the human is present or not, and I give this importance score to, if I can embed the importance score in the image, that will be much better. So for that reason, there are a lot of applications actually. I just say one example what came in my mind, but there may be lot example, because this network is widely used nowadays. So what they are doing is, here is a feature map X, which and from that feature map X, let's say there is another feature map from X to, they have done some convolution operation, and then they have get this feature map U. From U, what they have done, they want to give the activation, they want to do some classification, they want to do some classification, though it is not the final classification. They want to give a feed forward classification to give some attention scores or activations in the feature map. So for that reason, first what they have done is, they have squeezed the spatial resolution. So height and width will be squeezed using the global average pooling, and only the channels are left. So 1 plus 1 cross C. Now this 1 plus 1 cross C is now been provided with the sigmoid activation. So this is basically the sigmoid activation. So before sigmoid activation, what they have done, they have basically provided the ReLU so that nonlinearity is added, and then they have provided the sigmoid activation. So by that activation, it will say, let's say if you are doing human detection, it will say each of the image, each of the channels of that image, of that feature vector, whether it's contain a human or not, So this type of binary information will come up. So it will be 0 or 1 value. So that 0 or 1 value is then recalibrated, that is multiplied with the original feature map. So when it will multiply, that feature map is now having saying that which based on that on each of the channel, whatever they want. If it is a human detection, it will say our human detection. If it is saying something else, but it will say whether this channel says has that thing or not, so that it can replicate. So if when I take this forward for any classification, obviously or some other operations, okay, obviously it will confirm now that, because when I take average of this, or let's say max pool of the out of the channels, I will, if say let's say 90% says there is a human is there, and the 10% says there is no human, 10 of the channels says there is no human. So that means if I do a max pool, obviously say there is a human is there, so I am 100% sure the human is there, so it will not mislead. In case there is no human, I will take some other things to protect it. I will do some padding or something to protect it. So this is all about the deep neural networks. If you want to know more, you can read some of the papers of the deep neural. There are a lot of tutorials nowadays are available. However, see, reading the papers is easier rather than implementing them. So obviously there are a lot of tutorials are available for implementing them, but obviously it needs servers or GPU accesses. That is obvious there. But you people can start with small programs, and that will be useful. Anyway, if you have any doubt in deep neural network in future, you can contact me over my mail ID. Now we come to digital watermarking. So now digital watermarking, what does it says? So basically, I have a multimedia object. It may be audio, it may be video, it may be image, anything it may be, and I own it. Now the object is in the market, obviously it is in the network. So the hacker says it's mine and the owner says it's mine. So how we can define, how we can say, get a solution that whose object it is. So from there the idea of watermarking has come up. So basically in watermarking we can use some logo or some information which will be hide within the multimedia object, so that whenever required we extract it and get the authenticity. Now it can be of two types. One is visible logos. Say if you see Google and if you Google it, you will see a lot of images will come with a background. There some logo is there. The name of the company who has extracted will be there. So that will be a visible logo, a visible watermark. But the problem with that actually corrupt the quality of the images, right? So what that type of industry will do, they will basically, what they used to do is they basically take the watermarked image keep the watermark image in the network. But if you paid them, if you have a paid access, then they will provide you the actual multimedia without watermark. Other way around is we can have invisible watermark, and we don't give anyone with the original video or original image. Rather, I give the watermark version to everyone, and the watermark is invisible and it is imperceptible by human visual system. Imperceptible means it is not, we cannot perceive that yes, there is a watermark. So the quality is so good. So then, and it was given the network. Whenever required, whenever there is a problem, authenticity will arrive. What they will do? They will actually take out the watermark using some method and say yes, this is actually owned by them, this person or this industry, not by the others. So that was the more popular way rather than the first one. Because first one, again, when you go for the actual session, you are saying that you are going for actual images, then that means you have to, and in that case you have to give them the without unwatermarked versions, right? Because the watermark is visible. So obviously there the paid version is there. So if you have a paid something, or paid not only monetary but maybe some privilege opportunities are there, then only you will give them the unwatermarked version. Here everything is watermarked. We are not giving the unwatermarked version to anyone. And it is publicly available for all the publics. But whenever there is a problem of authenticity, we have the keys, we have the we have the location information that is called platelets. All these things we have. So all from them we will obviously get the finally we'll get the watermark for the authenticity. Now, digital watermarking will define it like it's a technology in which identification information is embedded in the data carrier in ways that cannot be easily noticed, and in which the data usage will not be affected. That means the quality should not be affected. That's why the data usage should not be affected, and it will be used for identification by embedding some data carrier. Fine. Obviously, it is used for copyright of the multimedia data and protect the databases and text files. These are very basic unit, basic information. So generally watermark has small repetitive information, and it is necessary to hide them from the viewers if it is an invisible watermarking. The next topic, since we have said the forensics, this is all about security. So I have also give a brief idea of steganography. So what is steganography is basically almost it looks similar to a watermarking. So in watermarking, what we do is we basically take care of the multimedia object where we embed some information which are for authenticity only. But steganography in other way around. Basically, we are hiding some important message in some multimedia object. So we care more about the multimedia, we care more about the hidden message that we are hiding them rather than the multimedia object. That is actually a cover up of that hidden message. So basically watermarking is used by, like, let's say movie makers or the industries, like we have pirated movies or not, whether they have watermark, from all these things we are using there. We are using for all this business purpose. Whereas this technology is widely used in military, it is used in medical sciences, all these places, especially in military forces, they use this, and this technology is being used from long back, even when there is no digitalization. Then also this military, this army and military people, they used to send their information in different forms of using steganography at that time, even drawing different images that have different hidden meanings, all this thing. So here, even the idea of embedding, extractions, if you see the techniques, they are almost similar, but the way out of both of them is the implicit meaning or the utility of both of them are completely different. So here we are aiming what is embedded, and because we want to extract exactly accurately what is embedded. But in watermarking, we are more about we have to claim the authenticity. So the extraction of the hidden data will be almost similar to the actual watermark. Then only we can get the authenticity. So, but we more care about the host image that should be available to all the in the public in the internet. Whereas here it should be that what happened with the host image, it doesn't matter, because that is just a cover up of for hiding the data that is in the hidden form. Now next, where it is used, obviously owner identification, authenticity, fingerprinting, covert communications, copy control, broadcast monitoring, and lot of other places. So fingerprinting, we know who it is, authenticity for authentications, owner identification, all these things are common actually. So I'm just skipping this part. Now let's come digital watermarking. So what we have is, we have a host image. We use the watermark to embed the information, get the watermarked image, and obviously we have the key. So key, I will say, is like as the palette or a key, that means that will have the locations where the watermark has been embedded. Then we have, when you want to extract it, obviously if it is a blind and if it is a non-blind, we will have the host image, we have the location, and finally we will extract the recovered watermark. Now what are the parameters that we will discuss, that we will need to be worried about while doing the digital watermarking? So first is imperceptibility. If I say it is a invisible, that we mainly use, and I am completely discussing here on the invisible watermarking. So imperceptibility, that means if the watermark is embedded also, the quality of the multimedia object should not degrade a lot. It should not be perceived by the human eyes. Even it should not be perceived by general systems also. Because if then perceived, then obviously if it's perceived means you can take it out, taking average or mean or some other type of filters, it will take out the watermark and he will reuse the image as his own. So that's why imperceptibility is one of the very important part in invisible watermarking. Next is security and robustness. So robustness says that if, let's say, if it is in the available publicly over the network, it is passing through different networks, so different type of compressions has been done. Some using some other type of compression, some using some other type of compressions. So different compressions are being used. Next, say not only that, there are different channel noises. There may be some other kind of noises. There may be some other, I am not saying very critical noises, but there's even smaller noises are there. There are some packet drops are there. All these things should not hamper the watermark. That is called robustness. In robustness means, given a set of attacks, our watermark can be perfectly extracted even after the presence of that attacks. The last one is the security. Security says that whether we should, when this, let's say the hackers have the, so till robustness we have the normal noises or the normal noises, let's say channel noise or additive noise or something like that, or compression noise. Security comes when there's a hacker is there. Let's say the hacker get the multimedia and he has a very good system also, very good system for extracting the for perceiving and extracting the watermark. He have still also he have the keys also. Still he cannot encrypt the watermark values. If he cannot encrypt the watermark values, he cannot remove it completely. So how secure should we make the watermark so that even if there are a lot of information is taken out by the attacker, still he cannot get the actual watermark out of the multimedia object. All this will again depend on the payload. Payload means how much of data I can embed in that multimedia object. How much of hidden data. Because as much as I will embed, obviously it will be more complicated. But obviously if it will be more complicated, then it will be more, the possibility will be less. So obviously if you see in the triangle, the lower end where the payload is higher, we have robustness and security. So obviously as we increase the payload, obviously the robustness will increase, as well as we have lot of places to encrypt and lot of things we can do, and the security, which will make the security more higher. But as we increase the payload, the imperceptibility will decrease. So visual quality of the host image will decrease. So that is the challenge that we'll have. So I already discussed these things. Robustness to survive accidental or malicious attempts. Imperceptibility, if the original cover video and the watermark are perceptibly invisible, indistinguishable. Payload, amount of information or the number of bits that are present, that present the watermark. Security, even some information of the watermark is known, one cannot able to remove the watermark by any chance. Visual quality, the embedding the watermark should not degrade the visual quality, that is imperceptible. Again, they are again in side by side. Complexity, how complex our algorithms are. Is it possible to actually implement them in reality? So obviously there is again a problem, there is again a standpoint where that we have to take care. How complex the algorithms are, because if we have to implement them in real time, then there should be feasible solutions. So obviously perceptual transparency depends on the payload, robustness and security, and all this thing again will come to blind and non-blind nature of the watermark. So we'll come how the blind and non-blind nature means and what their means actually. Now fragile, semi-fragile and robust watermark. Fragile means obviously there is a small change will actually destroy the watermark. Robust means it can withstand a class of transformation. Semi-fragile means in between them it can withstand some, but it can fail in unintentional transformations. Blind and non-blind is very important, because blind means it does not require the original image for extraction or detection. So when I am in the here, so here this layout show the non-blind extraction. See, we can see here as well as the watermark image, we need the host image. So in the early times when the digital watermarking has come up, people use the non-blind nature, where the watermark image and the host image both are required, as well as the key to recover the watermark properly. So that means the client where we have given for authentication, you have not only have to give the watermark version and the key, but also you have to give the unwatermark version, so that you get the proper, or you can extract the proper watermark, and finally you match the watermark for the authenticity. But this is not after some time this will not become very popular, because again if you have to keep the actual unwatermark version, then it's really a tedious job, and when you are spreading it, when you are giving someone for the authenticity, obviously it will be leaked out. So the next become popular is the blind version. So blind version says that we don't need the original image or the video, for detection or extraction. We have the watermark version and we have the key that is sufficient. Our algorithm is sufficient to extract correctly the watermark from that. Finally, compressed and uncompressed domain. So we have the watermark embedding is done in compressed images, uncompressed images, and in compressed images. So uncompressed images means normally if you see image or videos, they are in compressed version like .jpg or .avi. All these are compression version. So if you know that compression, JPG is like normally we use DCD. Then we use either if it's a lossy, then it will be there will be quantization. If it's not lossless, there will be no quantization. Then we'll have some encoding techniques. So obviously, if you say it is uncompressed domain watermarking, then obviously you have to first, if you get a JPG image, you have to uncompress it. Let's say in uncompressed versions, and then you have to embed the watermark and then compress it. Obviously, if you do an uncompressed in an uncompressed image or video, it will be good. But the problem when you do compression, it may go away. It may take away the watermark. So the next is compressed image. Now the compressed image, why will it will go away? Because there is a quantization is involved in while doing the compression. In lossy compression. Now in uncompressed, mostly we used to do some transformation. So obviously they are not the actual image. Now they have the coefficients, transform coefficients. Now if there is a transform coefficients, obviously on that coefficients we are going to embed. So you don't know how actually it's going to impact the image. So obviously there is a challenge of imperceptibility will come up. So here so nowadays mainly people think of doing uncompressed domain in watermarking, compressed domain watermarking rather than uncompressed domain watermarking. So we have multimedia objects like audio, video or image. So nothing to say about it. For compressed domain watermarking in videos, especially see in images there is nothing. We have a compressed image, nothing else. For videos, basically we have 3 types of frames: I, P and B frames. So I have in my PhD I have worked on basically compressed domain watermarking. So there we have basically dealing with the different type of frame types in compressed domain. There are I, P and B. So I is the intra frame, P is the predicted frame, and B is the bidirectional frame. Anyway, I have worked on like quite a few years back. It's almost like 6-7 years back. But still now people are working on this video watermarking, and especially in compressed domain. So I will just give a very brief idea about if someone want to work on it. Like that intra frames are the frames where the predictions for the compressions are for the compression has been done based on the intra blocks predictions. So these are least compressible because they are the prediction means here is basically we predict the difference between the blocks so that we can compress the number of bits. So there what they do is they will predict they will take the first block as a standard and will predict the difference between the other blocks of the video or of the frame, I will rather say the frame. Okay, so that all the values of all the actual values of all the other blocks does not needed to be kept, rather will keep the difference from the initial block. In P frames we'll do the same thing, but within not only within in a frame but also within the frames. So obviously that will be more compressed. And finally we have the bidirectional frames. So there the frames are being predicted, that means the difference has been predicted from the future frame as well as the previous frames. So they are more and more compressed actually. So it is good to embed in intra frames, that is I frames, but again as much as if you increase the payload, obviously it will affect the quality of the video. If you do for B frame, their mostly values are 0. Okay, so it is not a good, you will get very less place where you can embed, because you cannot change the 0 values. If you change the 0 values, obviously the bit rate will increase, then again there is no meaning of compression. So you have to only address the non-zero values. So there is a good place of embedding is in P frames. In my work I mostly work with the P frames. So that time, so because that has a lot of good place to hide the watermark and without affecting of the quality. So this was normally a group of pictures that is called GOP, and it will have a I frame with some B frame, some again P frame, some B frame, like this. It become a each of the each GOP is formed, and again these GOPs are repeated. For each GOP has one I frame. So we cannot keep a very big, normally we don't keep a very big GOP obviously, because that otherwise what will happen, if there is some error in prediction, that error will propagate for long and long time. Whenever there is an I frame, there is again the correlation between the frames will lost, and it will start fresh from that frame itself. So that's why the GOPs are not kept as much bigger in size. Now we'll come to the methodologies. So we have traditional methods. So in the traditional method, digital watermarking basically decomposed into 3 steps. First, some features are extracted from an image. Then they are modified to embed the watermark. Obviously, first extraction, then embed the watermark, and then they are projected back to the image space while avoiding the creation of the visual artifacts. So what we do is we have an original image. Now the original image will be embedded, right? So we have the watermark, original watermark. We have some error coding code, because we have to make it secure. We have given the secret key also, and finally we have produced the watermark image. Now how we can do it? So obviously we have to transform to do it, we may have to transform the original image to different way, right? So it may be we have some transformation, like let's say we have taken DCD features, or we have taken DFT features, different type of things we can take. Only taking the special domain features or special features like RGB values, it's not a very good choice. Anyway, so we have, first thing is original image, we have to transform it to somewhere where we can embed. Next is we have the watermark signal. We have to do some error coding, error correcting codes, so that it can be retrieved properly, as well as it will give some security. Next we have a secret key which will say where to embed. So the locations will be somewhere it will be shown by the secret key. And finally the watermark image will come up. Next we have the extraction. So while extraction, the key should be provided, but since it's a blind extraction, so we assume that the original image is not required anywhere. Now we have the key, we have the watermark image, and we have the error correcting codes, and finally we extracted the watermark signal. In special domain, what we have what is the transformation we can make? We can change the domain of the values. So one is, let's say we have RGB values, that is normally we can change to YUV. So these are the color space. I hope you people know that, right? Those who have idea of image processing, you know these are the color space. So initially in the beginning, because it is easier to embed in spatial domain, but though it was not very, I will say it is secure or robust to embed in the spatial domain, because anyone, if you can embed in the spatial domain, others can also extract from the spatial domain. So the hidden policy is not very good. But obviously it is easier. Why? Because you can view the image. So if I take let the image in RGB or YUV or HSV or YCBC or any of the format colors format, then and I embed it, then it will be easier to embed. So initially, if someone start with watermarking, they can start with spatial domain. Next is we have to transform the image. So obviously, see, one thing is normally the images are saved in the compressed format. Apart of that, if you transform the image, then what will happen? It will come, some of the features will come up, and if you embed in the features, obviously the attacker or the hacker will don't know what transform you have made, and if they doesn't know what transform you have made, it will be difficult for them to obviously to extract the watermark. So some of the very popular techniques that are used, more popular are transform domain watermarking is more popular than that of the spatial domain. So they use DCD transform that make the DCD coefficient, embed in the DCD coefficient DC and AC coefficients. Then they have take DFT, Fourier transform, discrete Fourier transform, discrete wavelet transform, fast Fourier transform, discrete Hadamard transform. All these are very popular techniques which are widely used in the in either in audio or in video or in images, in all the domains, these are widely used. Now, apart of that, I want to also mention that apart of that, we sometimes use, let's say, if we use a compressed domain. Okay, so in compressed domain, if we say we'll all see when it is compressed, we have only the bits. So if we say video compression, we have only the bits which is form of 0 and 1. When we transmit it over the channels, it is only 0 and 1. So if I want to embed 100 bits, it will not a good choice, right? So obviously it will, because of that one single bit change, we have a huge effect on the complete video. So what we do, we just make a uncompress it a bit. Bit means we come to the either to the till maximum, we come to the coefficient of from where we have transformed, or we come to the till the encoding part, coding part. Okay, so let's say we use Hoffman coding or arithmetic coding, some of the encoding techniques we have used, or there are a lot of other techniques nowadays, VLAC and all these things are there. So we are using some of the coding. Then so one way is encoding the coefficients, transform coefficient, but most of the video compression are lossy, even image are also lossy, like say JPEG, and mostly we have lossy so that we can reduce the size hugely, right? So if you embed in the coefficient, the problem is that when it is lossy, some of the watermark may also loss, and if the watermark are also lost, then how it will work? How will retrieve the watermark in the end? It's not possible. So some people also, apart of this transform coefficient, some people also love to hide the watermark in the while encoding. So while doing the coding with the from the after quantization, when they're trying to do encoding, obviously after that the bit rates will come up. But obviously there are lot of chances of doing manipulation with the image quality or the video quality. So we have to be aware. We have to find we have to use an excellent technique, excellent mechanism to find which parts can be of the encoding can be used for doing the for embedding the watermark. Now we come to the deep neural network. So deep neural network, I will not say is very popular in the watermarking. I will not say like that, but it was quite obviously used in digital watermarking. Though it was very popular in other fields, but it is not very popular in this area. So where are the areas we can use, where we can actually we can use the deep neural network? So one is feature extraction. So for the feature extraction, so after we extract the features only, then only we use the keys, secret keys, to embed the watermark. So that feature extraction can be done using the using deep network. Apart of that, what we have, as I told you earlier, the adversarial attack, right? So I have shown you there the generative adversarial network. So adversarial attack is basically where we have a watermark image. We are using the adversarial network to replicate or clone the watermark image with removing the watermark. So that is again a very dangerous attack that has been widely used by the generative adversarial network to attack such type of watermark images or videos. Now I have taken a paper. It is a very good paper actually. So this is published in one of the very well-known conference in WIFS. So what does it say? Are deep neural network good for blind image watermarking? So they have given analysis that how good the deep neural networks are for a blind image analysis watermarking. Is it clear up to this? Okay. So the layers of the deep neural network plays an important role, obviously, for extraction of the features and yielding the vectors for that needed to be watermark. So the feature extraction, earlier we do, let's say, some transformation, or we do some maybe some image processing technique to get the features where we can embed. Let's say we said we will embed the watermark only on the edges, because edges are highly likely not to be changed, so we'll use them. But again, obviously for that we have to use some edge detection techniques. Or if we say we are using in DCD domain, so we will transform in DCD domain and come back to the original image, kind of thing we used to do. So here we are saying that using a deep neural network, we'll find the features where we can embed. This raises the following challenges: how to invert these highly nonlinear extraction functions, because the extraction functions are nonlinear in nature, right? In the deep neural network, once the feature vector is watermarked, how to map it back to the image space. Now if I say I have to map it to the because we have to extract the feature map, now we have to go back the features to the original image. How it will be possible? Because obviously we have to return back to the image, that's why it will then only it will be finally be displayed, right? So how it is possible if you are using a deep neural network? Then how to take into account the perceptual model ensuring the quality of the watermark image. Next issue is how we maintain the perceptual quality, because the perceptual quality is one of the things that we are looking from all around all the time from the beginning of the watermarking process, right? So if I go for, let's say if I do some deep network and get some best robust features, but will that hamper the image quality? That question is there. Because the robustness is possible because we take very good features, but how we make that? Because see, the images will obviously change, the video will change, so the positions or the robustness will change from images to images. So how imperceptible it will be, or how the perceptual model will ensure that the watermark image is good, is in good quality. How to guarantee that a false negative, false positive label are as there is no probabilistic model to of these features. So how to guarantee? Basically, we have to guarantee that how we can decrease the false negative and we'll have the as false positive as much as possible. How we can decrease the false positives as much as possible, and we can have the positive results, only the true positives in our cases. So that is called false positive alarm. So we normally set some threshold that will say that if we extend that threshold, then we will say there is a false positive alarm. If there is an alarm, we will say now this technique is not sufficient enough to embed. So obviously we have to think of other methods where the false positive alarm should not be raised. So this paper that optical this paper is this one, the are deep neural network good for blind image watermarking. So there it composes a lot of mathematical analysis, but I have briefly described it. If you want to read it, you can read it from the paper itself. So what it says is there is a image called let's say I, and which we express it in the terms of x for each of the values over there. So D is a dual hypercone, which is basically D is the model where we are basically using the that is basically widely the D that is the basically we are getting the acceptance regions. So D is here the I will say the places where the watermark will be embedded. That are the regions we are founding through the D. So the image is denoted by I, that will show later on, and each of the pixels we are showing as value as x, and we have taken a model called dual hypercone. So that is again taken from the paper which is called optical watermark embedding and detection strategies under limited detection resources. So obviously if it is a hypercone, that means it is not a open-ended. So we have a limited detection resources. That's why it's called a hypercone. So the axis is A, and we say that if there is a region X which belongs to R to the power n, then the x to the power x transpose A will be greater than or equal to cos of theta, where the theta lies between 0 to pi by 2. So obviously that theta is the angle between the axis with the hypercone. So I think I should not discuss the mathematical part here. Rather I will say that what they are doing basically. So what they are using is basically they are watermarking the watermark an image using the embedded information. They have used 0 zero bit watermark. So zero bit watermark means is basically the watermark is not a logo or something. There are random bits and they are arranged properly. So they are zero bit watermarks. So these watermarks have been embedded here. So what the function? So they have checked the two things. It should be linear and invertile. So embedding this amount of the following. So they have taken argmax of Rx. So Rx is basically the obviously the regions where they have embedded x transpose A, p theta and minus of mod of x square. I think it will be too tedious to describe this mathematics so easily. So basically what they're doing, they are whenever they're embedding, what they're again, I will taking the features using some deep learning model. That features I will check with the mean square error or the PSNR. How is it affecting the mean square error or the PSNR? If they're not affecting much, obviously I will take it up for the embedding purpose. So that was the main idea for them. And while doing that, they are also checking the loss function, how much loss has been while in the deep network. They are also checking the loss, how much loss has been done. So what is the quality of the loss? For that reason, so let me skip this part because again they have lot of mathematics here. You can read the paper because anyway I will give come some this. So if the audience is okay for, because it will take some time, I don't know means how much time we have. Dr. Singh, can you just say, like, then I will go for a detailed discussion of this one. कैसे हो गया? Dr. Singh? I don't know how the internet has gone. Uh, so can we continue now? Can you please let me know up to which the internet was there? Okay, let me log out. I hope now it is fine. Okay, up to which? Still is echoing, right?
I think there is problem, some technical problem. So please wait 2 3 minutes. So now we should end this session, and I will ask ma'am to for her PPT and other related material. So we will join
Yeah,
at
sure, sure.
2 o'clock.
Just end up. I will just bind up. Yeah, I will just bind up now. Just
Okay, ma'am. Please, 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 please.
it's no okay, I'll just conclude it actually, because it's not showing the, I don't know, there's some issues with the internet, and now suddenly it's not showing the option for the sharing the PPT. So I will give the PPT that I will share with you, Professor Singh. Apart of that, so we have discussed basically the what the deep learning techniques we have. We have discussed the all the what are the watermarking techniques we can have. We have, though there are a lot of very few places where the watermarking has been neural network has been widely used in watermarking, but there are still a lot of scope where we can use this digital watermarking, use this deep neural network in digital watermarking. Now, the last was last. I was want to discuss about what we are doing. So, but I don't know why it was not, the PPT is not getting shared anymore. So I have to skip it now. There is no other option. Let me try it once so that I can discuss. So is it audible properly?